All right. Hey guys. So how's it going? It's again really great to see such great attendance to our section. Thank you for coming. Today we're going to go over substructural type systems and algebraic structures. And we'll be solving some problems in our section notes, as well as dive into the programming language of Haskell, a functional programming language similar to OCaml, but some different caveats. Before we get started on our section notes, I just want to quickly go over substructural type systems. And we're going to go over what are called structural inference rules and how we can manipulate these structural inference rules to result in what we call a linear type system. So just wondering, are you familiar with natural deduction? Yeah? Maybe? It's all good. So there's a concept called natural deduction. This does not write. Natural, okay, this doesn't write either. Natural deduction. This is a type of proof calculus where we can use to formalize sort of mathematical logic. And with natural deduction, it's very simple. You state certain facts that are true, and you say if these certain facts are true, then we can assume that this other fact is true. For example, let's say we have properties A1 through A2 ... to AN, and we also have a property called B. This in natural deduction means if A1, property of A1, where A1 could mean if the colors that we have are blue, yellow, and green. And A2 can mean if we have an amount of people in our set, let's say greater than 5, then our property B is true. So here this means if A1, A2, through AN all hold in a given context, then property B also holds. So this is similar to the logic, let's say we have the property P, and let's say we have the property that negative Q. So these are, again, all properties, certain facts about the world. And we say that, as a result, we have Q going. Yes. So we can say that if, let's say, we have proposition P as true, and we have the proposition negative Q as true, then the formula that if Q, and then if we have P, and then R, then this is true. This goes into more logic that's kind of out of the scope of this class, but these are just properties that we can take in the world and assume are true. And using this logic, we can write what are called inference rules and axioms for a given natural deduction calculus. And we can make these formulas into conjunctions, and we can play with natural deduction calculus with conjunctions. So we've already seen in this class inference rules and axioms where we state, okay, let's say the number 2 is a type int, and let's say the character C is a type string. We can play with what are called structural inference rules to result in certain types of other calculus that we would be interested in. And without writing these, I could just quickly pull it up on the screen. So here, here are 3 structural inference rules here. So they all look pretty intuitive. Let me get the laser pointer out. For our first structural inference rule, obviously we have what's called an exchange. And that says, okay, let's say we have context gamma, and let's say we have the property A and B, and then we have our set of types, delta, and then we say that if we have all these hold, then let's say we have the condition set C hold as well. But the thing is, it's exactly the same. If we allow the fact that we can say instead of A and B, we could say B, A, just change the order, then like the condition C holds, then that would mean, okay, we allow the property of exchange to hold. So similar but not quite the exact same structural inference rule is what's called a contradiction, where let's say you have the property A stated twice. And if you allow yourself to remove the second repeating A from your structural inference rule, then you have what's called a contraction structural inference rule. And a third structural inference rule is weakening, where you say if we have gamma and delta hold, then B holds. If that holds, then let's say if we were to add the fact that gamma, delta, and A hold, then B holds. So that's called a weakening, because you're adding another set of conditions in there. And again, as the course notes say, these are the other set of inference rules. This is obviously the first one, which says if A, then A. And then let's say another example one is if we have the fact that in context gamma, A and B hold, then B obviously holds. If we drop any of these structural inference rules here, then we have what's called a substructural logic. And the one that we're interested in for today is what's called a linear logic, where if we allow the property of like the structural inference rule of exchange to hold, but we don't require the contraction and weakening structural inference rules to hold, then we have what's called a linear logic. And what this results in is that it results in a system, a world, where every assumption you make must be used once. It's not that it can't be used, or it doesn't have to be used, or it has to be used more than once. No, you have whatever assumption you make, you have to make use of it once, but just once. And some examples are obviously what's called the affine logic, where we allow exchange and weakening but drop contraction. And this results in a property where all the assumptions that we make we can use more than once, or sorry, at most once. So this means that either you don't have to use all the assumptions you make, or you either don't use the assumption or use it once. But the difference between affine logic and linear logic is that in linear logic, whatever assumption you make, you have to use it exactly once. So let's quickly go to the section notes. Let's start doing some problems with this logic. So this problem references linear lambda calculus from lecture 17, which we're going to look at in just a sec. Let's look at the problem real quick. So suppose we extend the language with a negation operator, not E, where E is again an expression and not is the negation operator right here. And we know the fact that E needs to have a Boolean type, or the problem gives us the fact that E needs to have a Boolean type and the expression evaluates to E, or expression E evaluates to a value V. And that it evaluates to the negation of the Boolean represented by V. And it gives us a hint that the result of negation is what's called an unrestricted type, aka not linear. We're going to go into that really quickly. Write a type and rule for negation operator. So let's quickly look at this calculus that's referenced here. So this is the linear lambda calculus reference. Let's quickly look over these. Yeah. So the Q that we have here stands for what's called a qualifier, as the course notes state, where lin stands for linear qualifier, where it says if a given property is linear, then you have to make use of that property. But if it's what's called an unrestricted, shortened as un, then you don't have to make use of that property. And we have our classic Booleans, true and false, and these are all the list of expressions that we have in our language. So some new ones here are splits E1 as xy, x comma y in E2. Let's give a quick example of this syntax. So let's say we have split our expression E1, let's make it equal to 2, 3. Split E1 as xy. It could be AB, xy, whatever, xy in E2. And let's have our E2 be, we have to utilize x and y, or A and B, whatever we stay here in our E2 expression. Let's say E2 should be the fact that E2 should be equal to x plus y in E2. Intuitively, what this expression right here results in is where 2, or x becomes 2, because we're splitting a tuple with 2 elements. That's the condition here. Because here we stated only 2 variables, and our language only allows the fact that we can only have 2 variables here. So not 3, not 4, not 1, 2. So x becomes 2, and y becomes 3 in E2. So now we can apply x and y that exist in our expression 2 to get the result. And expression 2 is equal to x plus y. So this would be equal to 2 plus 3. And this long steps to 5 over, sorry. This is the, right? Yeah, this is the long step indicator for this. So we take our pair, our tuple, 2 tuple, 2, 3, we split into x and y, and then we applied an E2, which here was x plus y. So in the end, we get the result 5. So now, so this is clear, right? Yeah. So now let's look at 1a again. This is our language. Yes. So what it's pointing at is a negation operator, not E. To do this problem, we need to look at the inference rule given for Booleans for E. But here we could quickly write that as such. So how do our inference rules start with contexts? We always have, obviously, a line here where whatever we write at the bottom can only hold if our conditions at the top hold as well. So we start this with our context, which is shown as gamma. And we show that in context gamma, if, let's say, our expression E is, let's say, equal to Q bool, Q is again a qualifier. Q can stand for either linear or unrestricted in our linear lambda calculus language. Then for our negation operator, let's see, if we were to have an expression E and we know that the qualifier of this expression can be both linear or unrestricted, if we were to negate that, what would you expect our qualifier to be? Exactly. It says it should be unrestricted, but in terms of, let's think about this in an intuitive way. You can only, let's say if I were to give you lin true, would it be the case that I can use this expression that is equal to lin true at most once? Yes, because that's what the definition of a linear type is. But we can use this negative in however way we want. And as the problem hints to it as well, this is going to be an unrestricted variable. So the way that you write that here is as such. In context gamma, you have not E, because this should give you a hint that, like, if it's asking you to implement not E, then E will most likely be a Boolean, right? Because you can only utilize the language, the syntax not with a Boolean. So not E. And as the problem says, as the problem hints, it will be unbool. So what does this say here? This says that if in our context gamma we have an expression E that has type Q bool, where Q can be linear or unrestricted, then if we were to do the not of that expression, that will have a qualifier as unrestricted. So it can be both linear, so it's unrestricted, meaning it can be used not at all, it can be used only once, or it can be used more than once. And that's Boolean. So now let's say if we were to add in a new syntax to our language. If we were to add in let's pull this up here again. So again, this is our linear lambda calculus language. What if we were to add the conjunction operator? What if we were to add the operator and? What does and stand for usually? It stands for the wedge, right? And this is usually a truth operator, right? So let's say you have true and true. What does that equate to? True. Well, let's say if one of these are false, that is false, right? Yeah. Yeah, false, dot, 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 dot. Yeah, so now we will implement this exact same logic in our linear lambda calculus language. And if we were to operate the conjunction, if we were to add the conjunction operator and, where this will have two expressions around it, E1 and E2, right, where it can be true or false, how would we write the typing rule for this conjunction operator? Well, so let's look at this. Write an inference rule here. So how many expressions do we have in this conjecture operator? 1, 2. So this should give us an idea, a hint, that there should be two conditions, where E1 and E2 can exist under different contexts. Right? So let's say in context 1, it could be that whatever E1 is equal to, it results into a true value. But let's say in a different context, that same expression can result in a false value. So you always operate expressions under contexts, right? Because at the beginning, we didn't have contexts, so 2 equals 2, that's always true. But let's say now you have the fact, if x equals 5, then be true, x else false. In one context, x might be equal to 6, but in another context, x might be equal to 4 or 5. So your value for the Boolean might change. So we have to here think about the fact that we can have two different contexts. One context here, and then one context here, where we're dealing with our two expressions separately. We're given the condition that for our first expression, it has to be the fact that E1 will have type Q bool again, right? Because intuitively, a conjunction operator and this value right here will result in a Boolean value, right? So it's of type bool at the end, right? It's not going to be an integer or string, it's going to be a bool. So then we can think that E1 at the end and E2 in the end both result in a Boolean value. So this condition has to hold for context 1, because as we said, there can be different contexts that these expressions exist in. And then this is also the same fact. So here, notice that I marked E1 here with the Q qualifier and the E2 with the Q prime qualifier. This is to show that these qualifiers might differ. Am I saying it right, qualifier? Yeah, okay. Then, and we have to also have the condition that, well, let's not get too ahead. So now let's think about this. We established the conditions for E1 and E2. How should we establish the condition for E1 and E2, knowing that these two conditions hold? Well, as the question hints, the conjunction will be an unrestricted qualifier. So then that should give us an idea that in context gamma, where gamma is actually the composition of context 1 and context 2, this is how you indicate that. It will be the fact that E1 and E2 are of type unrestricted bool, but again, bool at the end. Yeah. So what the problem here is trying to show you that the sub-expressions here can be restricted, can be unrestricted or linear, and that they do not need to be the same. And that here we had to split the context again as context 1 and context 2, so that the linear variables in our overall context here are appropriately split between the computation of the sub-expressions. Yeah. So now let's go into our third question. 1C. So let us just display the question here. Yeah. So here we have the context gamma, which will have a variable x with type linear and then parentheses lin bool times unbool. And then the expression here, we have a split x as yz in this sub-expression here, which is E2. So again, this will be equal to E1 and this will be equal to E2. And the question is asking us whether E is well typed for context gamma. And it clarifies this, saying if under gamma, can E be equal to unbool, or can that condition hold? Yeah. So the derivation tree it's asking is going to be very long, so we don't need to write that and lose time. But let's look at this problem intuitively. Yeah. So we're going to go by highlighting the question here. So here, the type given to us is linear, and then parentheses lin-bool times un-bool. And here we're going to split the expression. So let's write this on the board. If we're going to split E into Y and Z, and here the type is given as lin-bool and un-bool, then we can intuitively think, okay, Y is expected to have the type lin-bool, right? And Z is expected to have the type un-bool, or unrestricted Boolean. And this does not need to hold yet. So let's write that here. Y will have the type this linear bool. And Z will have the type unrestricted bool. Yeah. So now the question's again asking, can the expression un-bool, can this value hold? Even though, let's say, what this statement here is saying that in a tuple that is considered linear, can we have an unrestricted Boolean inside? Or again, can we have an unrestricted value inside the linear data structure? This is the unrestricted value, this is the linear data structure. And the answer is yes, we can. And the derivation tree for this is as such right here. Even on the PDF, Professor Chung apologizes for the tiny font and advises us to look at the derivation tree, but this is how you can start. So here you are utilizing your inference rules that were declared in the previous lectures. And here you're starting with, okay, we have a variable z of type un-bool, therefore you have a type variable z of type un-bool. So this is like the identity factor almost. And now here with the question from 1a, we can say that, okay, if we have a variable z as un-bool, then its negation, not z, will also have the type un-bool, unrestricted Boolean. And the same fact for z here is repeated here again. And we have the fact, we have that y and z, where y is going to be a linear bool type and z is going to be an unrestricted bool type. With this, we can have the fact that y can have linear bool type. So why are we doing these like repeat declarations here and stating these obvious facts? Well, because we need to fill in the conditions for our if condition here. So if these three conditions hold, then we have that in the context where y has type linear bool and z has type unrestricted bool, that this if statement right here, if y then z, else not z, will have type unrestricted bool. So I want to quickly stop here and point out an obvious, a kind of not really too obvious fact. So if y then z else, let's say, a. So from an intuitive way, in an if loop right here, for y, what type does y need to be? Right here. Lin-bool, but even more intuitively, like y needs to evaluate to a Boolean at the end, right? It can't evaluate to a string or an integer.
Yeah.
Then what would you say about the types of z and a here? If we were to say that, let's say y is true, then we're going to be doing z, else we're going to be doing a. What would you say about the types of z and a? They should be the same. Why?
Well, because the entire expression either returns C or A, so when you're handling the result of the expression, regardless of which branch you follow, it should give something the same.
Exactly.
So you
Exactly.
handle it the same way, right?
Exactly. So, exactly. whatever expression you give it, you need to give the same expression for whether the condition is true or false or not, or the same type of the expression. An intuitive way to think about this is, let's say you write a program, a function that contains an if statement, and you return the result of whatever results from this if statement. So that means either you return Z or A. You can't have a function that can return different things, different types of things, right? Yeah, very nice. Okay, so let's go into our fourth problem now, which I think is the most interesting problem here. So let us look at this expression. So this expression here for 1D starts out as writing linear lambda x. So a linear type of lambda, we have a variable x that is of linear type. And the overall type of this, the overall type of x is going to be a tuple, where again, the overall type of the tuple is a linear element, but inside we have two unrestricted booleans. And this is the actual expression that we're asked to evaluate. Split x as yz in y, and then we're going to apply this in there. So it's asking us, consider the execution of this following well-typed expression, starting from the empty store. How would the final store look like? Here. Yeah. So one thing we know about linear types of values is that they need to be executed once, and at most once. So that means that for every single time that we execute a linear value, a linear object, that linear object will have a place of memory dedicated to it, to store that variable. Because the whole idea behind linear store types is that if you guarantee that some variable is a linear type of variable, then after you use that variable, you can then say, hey, I don't need to store this linear type variable again, because I know in my language that I will only be using this type of variable once. So you can get rid of that. You can save yourself from storing that linear type variable that was used once, because you know that that's only going to be used at most once. So if we were to break this expression down into what's actually being evaluated in the store, it will look something like this. I will be using L1, L2, L3, L4 to show what exactly is being stored in the store of, let's say, the computer that's evaluating this. The first thing that will be stored is this expression right here, right? Because this is declaring that the type of variable that we'll be using with. So linear lambda x and linear unbool times unbool. And then the expression that we have, split x as yz in y. So again, why are we storing this? Because it's a linear type of variable, and it's basically the first part of our expression. And then what will we do? We will be looking at our second expression given here, e2. And as this is a linear type as well, we'll be looking at the elements inside the tuple. So here again, we're storing values in our store, and we'll be utilizing these values. And the question is, what will the store look like at the end as we're evaluating this expression? So as we are asked to split x into y and z, we care about y and z here, where y will be on false and z will be untrue. So we'll be storing these two elements as well. So for y, we'll be storing on false. And for z, we'll be storing untrue, because we're going through the split statement right now. And after we go through our split statement, what we will have is, we'll be left with y at the end. And y here will be this expression right here. So linear, unfalse, untrue. So now we will then store this entire expression as well. It will be linear, unfalse, untrue, or L2, L3. Yes. So what do we see from here? We see that we are storing overall 2 unrestricted types of values and overall 2 linear types of values. Why? Because these 2 start with a linear, these 2 start with unrestricted type. And as I've said before, the whole purpose of the linear typing system is that once you utilize a variable, once you already store that variable in your store and proceed in evaluating your expression, you can get rid of that because your language guarantees that you won't be using that again. So what does the computer do? The computer says, okay, I already made a utilization of you, and I've made a utilization of you, and you, and you, and my typing, the rules of my system declare that I will not be needing linear types of values anymore after I use them. As a result, I can just delete this value right here. I can just get rid of whatever I'm storing in L1 and L4 because I've already used these types of variables and they are overall linear types of values. So then what this results in is, well, nothing. And again, well, nothing. But can it do the same for, yeah. Can the computer say the same thing for whatever stored in L2 and L3? No, because these are unrestricted types of values.
Could we go back a step? So
Yeah.
why is it, how do you know there are 4 things here? Like L1, L2, L3, L4, how do we decide what's what? So I see L1 is like the first expression.
Sure.
L2 is the Y, L3 is the Z. But how do you, why do you store those, not the X, for example? How do you just decide what needs to be stored and what doesn't?
How do you decide what needs to be stored and what doesn't? Okay. So, well, we have to store the type of our entire expression, which is this right here, before the period, basically. So that's your first intuition.
Which one does that correspond to? On the board? Wait.
Right here. So this corresponds to this part right here.
Parentheses, right? Yeah. Okay. That
Right
makes sense.
here.
Yeah.
Right?
Yeah.
Because you need to evaluate your expression. And the computer needs to remember that, okay, this is a linear type of, this entire expression right here is overall linear type. And the subtypes are unbool and unbool for the Boolean. So that's what you store first. And then you start evaluating the expression that you have here after the period.
Okay.
So that means you look at X in more detail, right? And what is X? X consists of the type given here, which is unfalse and untrue. So I see your question. It's actually a very good question because it's very hard to see, okay, like how does the computer go along and evaluate the expression? So the way it goes along is it looks at what it has first, right? What it has at first is, ignore this for a second. It has the expression that it needs to evaluate. It's looking at E1.
Why do we ignore that?
Why do we ignore this?
Is it because we're moving, like, we take the first expression, we try to evaluate it? Is that
Yeah,
kind of it?
yeah,
Okay.
exactly.
And then we evaluate, I see we have X, but we don't really evaluate X because we split that up, right?
Well, we evaluate
Or store
X. We make use of X, I would say, is a better way of expressing it.
Yeah.
Yeah, no worries.
But we don't store anything for X because we split it up. Is that correct?
We don't store anything for X because, yes, we are asked to split up X into the variables Y and Z.
Okay.
So we do store Y and the values for Y and Z.
Okay.
We just utilize X, we don't store it. Yes. Thank you for that question, actually. And yeah, so Y will be unfalse, so we're storing obviously the value for Y. And we're storing the value for Z. And actually here, it says split X as YZ and Y. So after the interesting thing here is after we split X into Y and Z, as you can see, we no longer make use of Z here because it's just asking to return what Y is. However, we are forced to store Z because it's asking us to split X into 2 specifically declared variables, Y and Z. So a comment that I would make here is just like with us, like as humans looking at this expression, we see that at the end we don't really care about what Z is, right? So then why are we storing the value for z? Well, the thing is the computer can't see this, and we did say that z will be equal to unrestricted true. So, and the computer says, okay, this type is this value is unrestricted. This means the computer doesn't know if it will be used exactly once or more than once or none at all. So it can't get rid of that in the store. But but what it has for the expression here overall, which is a linear type, and what it has for x overall, where it's linear, unfalse and untrue, it knows that, okay, the overall type of this is linear. That means after I make use of it right here at split x, I can just get rid of it. Does that answer your question?
Yes. Great.
Okay, of course. Cool. So now let's progress into the second question, where we go into questions from lecture 18, algebraic structures. Yeah. So to do this question, we need to look into the lecture notes where it is defining the function map. And that is right here. Yes, right here. So before we progress further with this question, I just want to quickly go over the map function. Have you used it before, the map function?
In this class?
Mm-hmm. Or before? Are you familiar with it?
Or like just in general programming?
Yeah.
Yes, yes.
Okay.
Like, yeah, you have a list of, I guess, variables, and you just apply the same function to
Those variables, yeah.
variables on the element.
Exactly. So just to give a quick example, if I were to write this, map plus 2, and we have a list 6, 7, 8, what will this return?
8, 9, 10.
Yeah, 8, 9, 10. What did we do here? We applied our plus 2 function, which expects how many inputs? How many inputs does this function here expect? Because plus 1, right? Because 2 expects 2, yeah, exactly. So the map function, exactly how you said, takes in a function that only expects one value and applies it into a certain list of variables. And these don't need to be integers. They can be strings, booleans, or your own custom types. Yeah. So let's look at the formal declaration of our map function. Yeah, and this is the type that we just said. It expects one input of type A, and it returns B. And then TA here is a type constructor. And in this example that we gave, TA stands for, let's say, a list of items, 6, 7, 8, A, B, C, red, blue, green. Yeah. It takes in a function from A to B and an element of TA, and returns an element CB. Yeah. And now we need to show that the option type, with map defined in the lecture notes, satisfy the function laws. To go over this again, to go over this other example, are you familiar with the option type?
Yes.
Yeah.
Either be none or be
Something, right? Yeah. So let's say, what is a example of a thing in real life that can be either nothing, none, or something? Let's say number of chairs in a room.
Okay.
I don't know, num chairs. There can either be no chairs in the room, right? So either it's none, or in OCaml, the way we state this is some x, right? Where x is of type int. Yeah. So now we will show that the option type satisfied the functor laws for function map. And honestly, the way we do that is like this. Let's go over the solutions, actually. Here what we're given is, we have two functor laws. And what are functors? Yeah. Functors. As the lecture note states, it's an algebraic structure that associates with each set A a set TA. And you could think of, again, T of A as where T is a type constructor. So an element of a list here, right? So it's an element of an even bigger expression, of an even bigger item. And here in the lecture notes, it states that there are two functor laws where, this is pretty complicated one now, but what we have is that we need to show that the properties of distributivity and identity hold for the option type. And the way we do that is like so. We first give the definition of the map type. By the way, you won't be quizzed on this in either the homework or in the final. This is just to show kind of the intuition behind the option type with the map function. Yeah. Here we have the function map, where it expects a function of type t1 going to t2, aka, let's say in our example, +2, and an element, t1 option. So yes, what we now have here is, instead of, let's say, just having a list 6, 7, 8, we have perhaps this condition, map, same thing, +2. And now we have, let's say, sum 6, right? Sum 7, sum 8. At the end here, it's pretty intuitive what this will result in, right? This will result in a list sum 8, sum 9, sum 10. However, we are, for the purpose of this question, just showing that even if we were to have the option types, we can still show that the map function holds for when we integrate our option types. This is the whole purpose of this question. And here, I guess I did it in a proof by construction manner, where yes, this will result in a sum 8, sum 9, sum 10. But this is the formal declaration of this. And the long part of this question is showing that the distributivity property holds, where you start with this expression right here, where you have option, and then you have the values map G and map F separately, and then at the end you show that, okay, now we have map on the outside, and we have F and G applied inside in this manner. I would say it's pretty boring stuff. And then for identity, it's actually a bit more intuitive, because let's say you were giving the function lambda a with type t, going to a again, right? You want to end up with an expression where now it is exactly the same function, except now you have t option, because if you can have 6, 7, 8, it's pretty clear and intuitive to us that you can also have sum 6, sum 7, sum 8. So this is the formal declaration of that. Yeah. So we can skip over this question and actually go into the question that actually matters for this section notes and for our homework, because I believe for either this P set or the P set after, you'll be working in Haskell. Yeah, the next one. So let's go over my favorite part of this section, which is learning the Haskell language. Yeah. So now I'm going to transition into a screen with a programming editor, code editor, as well as, yes, this is Visual Studio Code, my recommended choice of, of text editors / everything editor. So on the left, I have Visual Studio Code, and on the right, I have just a terminal iTerm running.
Does Haskell have a command line?
Yes, it does. First, have you installed Haskell yet on your computer? You have? Okay. So open a terminal on your computer. The way you pull up the integrated terminal of Haskell is by typing GHCI. Done. Let me zoom into this too. Zoom in. Zoom in. There we go. Yeah. Did you get it on your computer?
Maybe I have not installed Haskell.
You have not? No worries. I can show you how to quickly do that. a very nice way of doing it is go into the lecture notes and then go into the link that is provided here. Download Haskell platform. Oops. And if you're like most Harvard students, you probably have a Mac, so you just need to download the file given here and run through the installer. Yeah, let me know when you get that, because I'd like to do these examples together. No worries. All good, all good. I can come and help you if you want.
It's all good. It's pretty, I think it's pretty true.
Yeah.
Is there a way I can test if it's installed other than?
Writing in the terminal GHCI. I would say if you have it installed and it's still not working, once you type GHCI,
Okay, probably.
open up a new terminal because it needs to refresh the list of like available commands
Yeah.
to you, right? Are you familiar with like a bash profile /etc/profile?
Yeah.
Yeah,
Vaguely familiar.
yeah, yeah. Those two files that I just like said are basically ways for the computer to know what you're talking about when you give it acronyms.
Yeah.
Yeah. So while you do that, let me just show you the beauty of this language. Oops, oops.
There we go.
Okay,
Yes.
got it?
Yeah.
Okay. So, as I've said before, Haskell is a Haskell is a functional programming language, and it makes heavy utilization of what's called lazy programming. Are you familiar with lazy programming?
I've heard of it. I forget what it is.
No worries. So lazy programming is when basically you're asked to, where the programming language or the program platform only evaluates certain expressions when it is absolutely forced to evaluate it. For example, if we were to remember earlier sections, we talked about call by need versus call by value, where in one you evaluate the expression immediately, and in another you kept transferring the unevaluated version of the expression from one application to another, and you only evaluate the expression at the end. The beauty of this language is that it does exactly that, and it remembers the results of things that it evaluates. This comes in very helpful for certain applications, such as factorial, the calculation of factorial numbers, right? So let's just quickly go over an example of this. So obviously, what are factorial numbers? It's basically when you have, let's say, a factorial number n, and that is equal to, right, fact n minus 1, factorial of that number n minus 1, plus factorial of n minus 2. Right. The thing is with this, let's say you are asked to evaluate the factorial of 5, right? This will result in you evaluating the value for fact 4 plus fact 3, right? And this will result in, F3, F2. Exactly. But let me just show you this part, F1. And let's say you know that fact of 0 is equal to obviously 1, right? And fact of 1 is also equal to 1. So the thing is here, you are asked, I didn't even draw the derivation tree for this. Just for fact 4, you were asked to evaluate the value for fact 1 3 times, and you're asked to evaluate the value of fact 2 twice. With lazy programming, what happens is the computer says, okay, let me do all these calculations. Let me do F1, factorial of 1. Okay, that's equal to the value of 1. Let me do factorial of 2. Oh, that's equal to 1 plus 1, 2. So when it comes here, again, and sees that it's asked to evaluate fact 2, it doesn't do 1 plus 1, no matter how insignificant that calculation is. It says, wait, I've done this already before, it's just 2. So it remembers what it calculates. It remembers what it's done before, and then quickly gives you the result of your of that function rather than doing the calculations. Obviously, the speed performance of factorial 2, where you recall from memory or where you calculate it, is almost exactly the same. But if you're asked to calculate the factorial of 50, this is going to be a number where you're going to be doing 49 plus 48. Okay, now that's 48 plus 47 plus. There will be a lot of subtrees that result. And the amount of times you'll be doing the same calculation for the factorial of 45 will be way greater than the amount it will take you to just do that calculation once and then you reuse that. So just bear with me here. Let's write a quick factorial function in Python where, just to give it a quick example. Let's say fact, where we taking xy, right? If, let's say, or we taking x, right? So how would we start this? This would ask us to give if x is equal to 0 or x is equal to 1, then we return 1, right? Oh, sorry. Yes, thank you. I'm a senior doing computer science, I should know this.
Yeah.
Else, if it doesn't result here, what we do is just fact.
Return.
Return.
Return fact, or I guess we're doing Fibonacci, but sure, fact x minus 1, x plus x minus fact x minus.
Yeah. So the reason why I'm doing this very bad implementation of this is so that we can demonstrate how long this takes. And this is it. Print fact of, say, 5. And here I will have a new terminal. Actually right here, desktop H. So let us do Python 3 fact.py. This will evaluate pretty quickly, right? 8.
Yeah.
Okay, so that was pretty quick. Even though we did this in a very lazy way, where here we are forced to recalculate the values over again. We're not saving anything 8. But if we were to do factorial of 41, say it's taken a lot of time.
Yeah.
Why is it doing that?
2 to the 40, a massive tree, basically.
Exactly. Now let us do the same thing in Haskell with lazy programming. There are 2 ways we can do this. Either we can write in our interactive terminal here, where we say, I already did this before, can I not do it again? Okay, where we can either do it here, so we can say let fact n equal, if like n is equal to 0, or n is equal to 1, we can continue to implement this in our interactive terminal, or we can just write it in a normal file and then get the result that way. I would much rather prefer this because we can do more quickly. So ignore this part of the code here for a sec. Let's focus on just these 2 lines right here. Fact 0 equals 1, and fact n equals n times fact n minus 1. Or wait.
So do we need to define fact anyway?
We are defining fact here.
Oh, that's
Exactly.
definition in itself? That's cool.
Yeah. Exactly. This is how you can do it. Yes. So there are different ways of actually declaring a factorial function. This is one way of doing it. You say factorial of 0 equals 1, and a factorial of n equals the case where it's n times factorial n minus 1.
Right. Right.
And then another way of doing it is...
I see the line above it. Is that necessary? Like line 18? Is that necessary?
No, it's not necessary. No,
Okay.
no, it's not necessary. Yeah, it's not necessary. It figures this out automatically by itself.
Great.
And then there's another way of doing it where it's factorial prime n, where it's case n of, right? This is match n with, exactly. Exactly. So if we were to do this right here, let's see, in our current folder we have,
Does white space matter in Haskell?
No, it does not, to my knowledge.
Then how does it distinguish between like the two cases for
Oops. How does it
like,
distinguish?
in case n of, and then it's 0 arrow 1, and then n arrow something else. So how does it know?
Right here, you mean?
Yeah, like how does it know whether it's 0 or n? Like what happens if you just like put it on the same line, for example?
Oh, well, it's the same thing with OCaml, right? It goes on.
Oh, right. Actually, never mind. Yeah, OCaml's fine.
Yeah, OCaml's fine. Because it figures out, okay, if I say an arrow, that means it's another case for the, that's another
Oh,
possible
right.
case
Okay,
given.
yeah,
Yeah. And so the way, oops, as you can see, these are all my errors that I've got while compiling this. This is, so let's actually go over the interactive terminal. So again, we write GHCI. It's very simple. You can do 2 plus 2 for print hello, hello. And you can also do stuff like let factorial n is equal to, or let's say let sample function x is equal to x plus 1, right? And then if I were to say sample function 5 or 6, it should return 7. So this is how you can declare it. And you can also have stuff like let sample function 0 equals 0. So now if I were to do sample function 0, it returns a 0. But if I were to do sample function, again, 6, it says non-exhaustive patterns in function sample function. Because what happened here was,
Kind of match 6 to 0, but can't do that.
exactly. I overwrote it. And yeah, so now let's look at our factorial functions again, which we will do in our pre-written code. The way you compile given Haskell file is as such. You write GHC /o, and /o is just cleaning up all the build files that result. You give the name of the binary you wanted to save into. So since my file name, whoops, sorry about that. Yeah. Since my file name is simple. Yes, .hs, yeah. And the way you make comments in Haskell is just two dashes.
Okay, great.
The way you do that is you give the name of the binary, sample, and then you just give the name of the file, sample.hs. So this compiled correctly. If I were to make a mistake, it's going to be like, what are you doing? Parse error, modulator, import declaration, whatnot. Yeah, it even highlights the part that you think you did wrong on. So just delete that. So now the part comes where we run the file. Have you ever worked with C before?
Yeah.
Yeah. In C, how do you run files?
Or I guess you compile it and then it
And then-
generates the native executable.
Exactly.
So it's like just /.
Dot slash, here we named it sample,
Yeah, executable.
done.
Yeah.
This is it.
Oh, that was fast,
Yeah, it was really fast. Has our Python thing finished running? Oh, it has. Interesting. But the thing is here, we are doing multiplication. How could we turn this into the actual factorial function?
Like the Fibonacci,
Yes.
I guess. Fibonacci would be
How could we write a Fibonacci function?
fact.
Or not fact, let's say fib. Let's write it together.
Fib n equals to,
Let's do the base cases first.
or oh sure, yeah, right, I forget. That's kind of weird. Okay,
Uh-huh.
fib, like 0 equals 1, 1 equals 1.
Yeah.
Yeah.
And?
And then fib n equals fib n minus 1 plus fib n minus
Yes. That was pretty intuitive, no?
2. Yeah.
Yeah. And now, when you write code into a Haskell file, you have to define a main function, because that's what the executable is looking for. That's what, the compile is looking for. So like if I were to delete this,
Okay.
if I were to try to compile. Oh, it compiles, interesting. But it usually looks for a main file.
Okay.
Yeah. Oh, so obviously if I were to delete this, yeah, it wouldn't print out the file. Because here we're just declaring the functions, but we're not doing anything with it. Yeah.
I guess it's like Python too. Like you can provide a main function, but you don't have to.
Exactly. So if we were to do Fibonacci of 42, let's even keep the factorial of 42. And let's run this. Let's compile it. Let's run it. Uh-oh, what's going on here?
Oh, let's see. to do something special to
Yes.
do the lazy
Yes.
programming? Okay.
That's exactly what we need to do. Because here we wrote it in a way where it's calculating values over and over and over again.
Okay.
So the way we will do this is I will cheat and show you how the pros do it. As such. And this is the way that we did it as well.
Yeah.
Yeah. So this is calculation factorial. Wait. So this is what we wrote here, right? Fibonacci of 0, Fibonacci of 1. But it's still doing the calculation. So this means, do you think this means that we've implemented lazy programming?
Probably not.
Probably not, yeah. So we need to find a way in which we actually do implement lazy programming. And I had this code here somewhere. Fib. Yeah. How about this? We look up Haskell. This is the beauty of programming. Lazy. Yeah. There we go. So this is exactly what we did. But why is it the case that it's still taking so long? It's still taking a long time. It's still calculating. I think our Python function even took this much. But this is doing it for 42. So if we were to do it for 41, how fast would it be? Because I believe there's a point in time, I think it's either 41 or 42, where the time of the program goes from a few seconds to a few minutes. Yeah. I believe I had it here somewhere. Interesting. Yeah. Okay, all good. Then we can just progress into doing some of the section notes actually. Yeah. So I guess we got familiar with Haskell a bit, and we did some functional programming, which is where, again, functional programming is literally where you say, this is our function fact or factorial or Fibonacci, and if this is the input given to us, then it's the result that we give. These are the base cases, and these are the recursive cases. So we wrote the factorial function. Let's write the append function for lists. And the beauty is we already have that written. Great. So what's the logic of this? The logic of this is, so let's look at my append right here. The type of my append is you're given two inputs. A here stands for prime or quote, right? Single quote, A and O camel. You know what that is, right? Yeah. That's basically where you're saying it can be any type. So here my append is a function where it takes an input of type list with any type, and then another input with type list of any type, and it returns a final list with that same type. And the inputs that you have here are all of the same type. And you have my append in this example here. This is the base case. You have empty lists, and you have the variable x, where x is the list, and you have x itself. And the recursive cases here is you have the list xxs. What this indicates is like this. So you have your list, again, let's say 5, 6, 7. What is the head of your list here? 5.
Yeah.
What is the tail?
7.
The tail.
Oh, sorry, 6 and 7.
6 to 7.
Yeah.
So why is it 6 to 7 and not 7?
It's like the rest of the...
Right, exactly, exactly. So let's actually do this my append function here on the board. Let's see how it works. So we have my append x colon xs, where x is the head, xs is the tail. We can easily change this with head and tail. And then we're given y. We are asked here to do the recursive function for this. So if 5, 6, 7 were to be my list, and y would to be equal to 8. Oops, that was really bad. Yes. What would we have happen? We would have our first element here, 5, right? What does it equate to? 5 colon my append XSY, right? So what this would be is 5, and then the function my append, the list 6, 7, and then 8, right? And what would this go into? This would go into 5 colon 6 colon my append with the list 7 and 8. And what would this go into? This would go into 5, 6, 7, and then my append, empty list, 8. And finally, this would result in 5, 6, 7, and 8. And what does this give us at the end? 5, 6, 7, 8. So, yeah. So how was this added? So how was 8 appended to the list? It was appended by going through every single element in the list in a recursive manner and added to the end. So this was the intuition of this recursive function. Yeah, and I encourage everyone to go into the remainder of the section notes. And we didn't have time to go over monads or the bind syntax, but definitely go through some of the Haskell code given here in the course sections website, where there's some sample Haskell code. And this will be really useful for the homework problem for the next P set, where you're asked to implement a few functions in Haskell. Yeah, I hope you enjoyed this section. See you guys next time. Bye-bye.